And we should have had a label. We should have had a big label saying it's not molasses, not a whole milk. Gallon of whole milk, like, not very big like that.
I spotted it.
Yeah.
Okay, awesome. So I think we can get started. So hi everyone. It's our pleasure here today to have Tianhong Lu from Emory University. He did grad students with Luis Santos, and he'll be telling us today about the composite fermion approach to fractional Chern insulators, in particular in twisted MoTe2. So take it away.
Okay, thanks. Good afternoon, everyone. My name is Tian. I'm a third-year graduate student at Emory University. So first of all, I'd like to thank Dr. Leather for inviting me to present a recent work in our lab at Emory with my advisor, Luis Santos. So can you guys hear me clearly?
Yeah.
Okay, thanks. So the title of my slides is Fractional Chern Insulators in Twisted Bilayer MoTe2, which is also the title of my paper. So I have to say that I'm not trying to be lazy here. I think the title itself is pretty concise. Fractional Chern insulators is a fractionalization phenomenon that was predicted in theory about a decade ago. And recently, last year, it was finally observed in experiments in a system called Twisted Bilayer MoTe2. And in this work, we'd like to see from a composite fermion perspective to show that Twisted Bilayer MoTe2 is a system that has rich FCIs and quantum phase transitions. So there are 4 components in my slides. First, I'm going to start with experimental observations of fractional Chern insulators in the system Twisted Bilayer MoTe2, or for simplicity, TMoTe2, is a MoTe system and also a transition metal dichalcogen materials, which I'm going to introduce later. And then I will introduce an effective lattice model for the valence bands, because in experiments, they will dope the system with holes. So valence bands are what they're interested in. The main part of my slides would be how we use composite fermion theory to depict a family of FCIs where fractionalization is heavily influenced by lattice effects, and also how the quantum phase transitions of FCIs interplays with a higher order Van 't Hoff singularity. At the end, I'm going to show some interesting directions we're currently exploring or would like to explore. Okay, so the idea of fractional Chern insulators, or FCI for simplicity, was proposed in 2011. Basically, is fractional quantum Hall effect without magnetic fields. So imagine in Landau levels, a uniform magnetic field creates quantized flat energy bands, and each band carries a Chern number 1. When you fill integer number of those bands, you get integer quantum Hall effect. When you fill a fraction of the band, interaction will lead to a fractional quantum Hall effect, fractional quantum Hall conductance at different specific filling fractions. So this is great, but we don't have to have an external field in order to have those non-zero Chern numbers. FCI is a system on a lattice. It can be any kind of lattice, usually with staggering fluxes, but on average, the fluxes or the field is 0. FCI breaks time reversal symmetry spontaneously by developing bands with non-zero Chern number. For example, here I'm showing a simple illustration, just a demo. We have 2 bands, and each band carries Chern number 1 or -1. When you partially fill a Chern band, interaction will lead to fractional quantum Hall conductance, and this conductance is usually proportional to the specific filling fractions. So this whole thing is predicted about a decade ago. Finally, there are exciting experimental observations in real life last year. So fractional Chern insulator was proposed in lattice system, but it didn't mention, or it didn't require what the scale of the unit cell should be in order to realize FCI in the lab, because a lattice constant could be just symbolic in the theory, but in experiments, an external field, B field, is still more or less being used to, for example, probe the system, to maybe break the time reversal symmetry slightly. So we still need to compare the magnetic length versus the unit cell length. So if in conventional lattice, if the magnetic length is much larger than the unit cell, then maybe you might not be able to get FCI, maybe you just get Landau levels instead, because the magnetic length overlooks the scale of the unit cell, as if it's a two-dimensional electron gas. So a MoTe lattice is created by overlapping multiple layers of lattices with a small twist. So in the experiments, the system is twisted by their MoTe2, which means we have 2 layers of MoTe2. As you can see, the resulting, so here in the figure, I'm overlapping 2 honeycomb lattices, and the resulting MoTe unit cell is much larger than that of the individual layer. You can see probably maybe so there are many unit cells in the individual layer, but here I can maybe count 6, 7 MoTe unit cell. And that's exactly what we need. We need a large scale of the unit cell. And the resulting MoTe Brillouin zone is much smaller. So when we shift lattices in the real space, the momentum space is also being shifted. So there are 2, so in the figure below, there are 2 large hexagons, which each represents the first Brillouin zone of the individual honeycomb lattices. And when there is a tiny twist, the high symmetry point, for example, K point, from the 2 layers, which we call KT, K top, or KB, K bottom, is shifted by a small distance. And this distance makes one edge of the MoTe Brillouin zone. And the resulting MoTe Brillouin zone is still a hexagon, but it's much smaller. So TMOT2 is a MoTe system, and an individual layer, which is MoTe2, is a transition metal dichecogeni material. We're not going to get into the details of this material, but the takeaway is, so the takeaway of this material is a semiconductor. So below the Fermi surface, it's the valence bands are gapped from the conduction bands, and it's kind of like parabolic dispersion pointing downward. If we get close to the K point, we find the topmost 2 valence bands carry opposite spin, spin down and spin up. And if we move close to the minus K point, which is also another high symmetry point, the topmost 2 valence bands carry spin up and spin down, which is a time reversal copy of the K point. And if we have a bilayer of this material, bilayer TMD, and first just keep the 2 layers independent from each other, we just get 2 copies of them, right? And in experiments, time reversal symmetry breaks spontaneously. So if that breaks spontaneously, we just need to focus on one spin valley. So this is called spin valley locking. For example, we just need to focus on K valley with spin up, because that's the closest to the Fermi surface. The other spin valley is the time reversal copy. So because of the encapsulated nature of the MoRe sample fabrication in experiments, we haven't seen a direct measurement of the energy dispersion of MoRe lattice in experiments like RPES. But people have obtained the MoRe bands with the help of numerical calculation. It's called density functional theory. Here I'm showing two DFT results from two papers. One is at 1.2 twist angle. The other one is at 3.89 twist angle. They're both for single valley and spin because spin and valley are locked in this material. So no matter if it's 1.2 degrees or 3.89 degrees, one common thing is that the topmost two valence bands carry a pair of Chern number +1, -1. So from the theoretical point of view, it's highly possible to find FCI in such systems. And in fact, it's been observed last year. Now I'm showing some excellent work of experimental observation of FCIs in MoTe2, and one of them is by a group at Cornell. I have to mention that. First of all, the experiments were performed by adding or doping holes in the MoRe bands. So electrons can be viewed as a background. But how do people actually make sure when a MoRe band is entirely filled with holes or just a specific fraction, right? The definition is pretty straightforward. When the filling fraction is 1, I'm showing -1 because negative shows that it's hole doping instead of electron doping. If the filling fraction is 1, it means 1 hole per unit cell. If it's a fraction, it means a fraction of holes per unit cell. Or, for example, if the filling fraction is 2/3, it means on average you have 2 holes every 3 unit cells. So the first result shows you the measurements of longitudinal and transverse resistance at filling fraction 2/3 and 3/5. And this material has twist angle 3.7. You can see that, so in the first row of the figure, it's longitudinal resistance. You can see that this is about 0, which at all times. This is a common feature of quantum Hall effect. And the very exciting thing is in the second row of the figure, the transverse resistance, or what we call it Hall resistance, is quantized to a fraction. For example, in the first column is quantized to either ±3/2. In the second column is 5/3. So these two fractions are actually the inverse of the filling fraction. And the second row of the figure is showing you a hysteresis loop of the transverse resistance. So FCI doesn't require an external field, but with the help of a small probing field, you can flip the direction of this, flip the direction that spin wants to align with. So for example, if we look at the second row, the first column is the 2/3 filling fraction, and moving from left to right, it's the direction of the probing field flips. That also flips the direction that spin wants to align with, that resulting in the electron transport in the opposite direction. The second work is performed at Cornell, so I hope I can explain this well enough. The second work provides another perspective. It tracks the incompressible states in the system at about 3.4 degrees. Why? Because when FCI state is formed with interaction, it will create a gap between themselves and other states, and they become the incompressible ground state. So by tracking those incompressible states, we can locate where FCI is. In the figure, the incompressible states have a linear dependency. It's linear dependency of external field versus the filling fraction. This is described by a formula called Streda's formula. It's saying that when you have a Chern insulator or fractional Chern insulator, the filling fraction of the ground state will linearly depend on an external field. And the slope T here reflects the Hall conductance. As you can see from the figure, when the B field is approaching 0, those two lines is approaching the two filling fractions 0.63, which is 2/3 and 1. And the slope is the slope is also 2/3 and 1 respectively. This is indicating that you have a fractional Chern insulators at 2/3 hole filling and a Chern insulator at 1 filling. So if you have any questions, please just stop me and ask the question. Okay. So at this point, you might wonder what is the difference between moire bands and Landau levels, since we've seen fractionalization in both of them. This difference actually raised the key question that our work is going to investigate. Moire bands host FCI from band topology. It doesn't require an external field. And the scale of the Moire superlattice is nanometer. It's heavily influenced by lattice effects. Landau levels host fractional quantum Hall effect created by magnetic fields. And the magnetic length is also nanometer. It's much larger than the atomic separation, which is angstrom in conventional lattice system. A key question we'd like to ask is, how does lattice effects impact topological phases with fractional quartz particles?
Question?
Oh, yeah, sure.
What specific type of impact are you going to be looking at?
For example,
fractional statistics, or I don't know, what aspect?
So for example, we're looking for how the lattice effects of impact the quantum phase transition in this FCIs.
Quantum phase transition between what and what? What phases?
So I'm going to introduce later, but for example, lattice parameters will impact the composite fermion gap. So with gap closing and reopening, there is quantum phase transitions.
Thank you.
Okay, thanks. Okay. Okay. So here I'm going to introduce a lattice model, let's see, yeah. Function Wu and others proposed a two-band lattice model, which is a Haldane model that respects the symmetry of the honeycomb lattice, which is also the symmetry of the MoTe2 lattice. And they fit this to the DFT bands very well. They first start with the continuum model that includes 2 layers at a single spin valley and add tunneling between the layers on the off diagonal. As you can see, because of the spin valley locking, we can just pay attention to one valley with one spin. And this is the illustration of the momentum space twist. So as you can see in the illustration, when 2 layers are twisted by a small angle, the K points from the 2 layers shift a bit. And that shift is reflected on the diagonal terms. I'm not sure if you can see clearly, on the diagonal terms, there are 2 parabolic dispersions. And in one of them is minus K plus. In the other one is minus K minus, which is K, KB and KT in the figure. So it turned out that this shift in the parabolic term can be cancelled with a gauge transformation. And that gauge transformation eventually became the phase factor for the second neighbor hopping in the Haldane model. So the phase, yeah. So this is the tight binding model they got from the continuum model. And it's a Haldane model with first neighbor hopping and second neighbor hopping. There are two hopping parameters. T0 stands for nearest neighbor hopping. T1 stands for second neighbor hopping. The nearest neighbor hopping is real. The second neighbor hopping has this Haldane phase, which is fixed by the symmetry. It's 2 pi over 3 plus minus times the spin. And there are two indices in the model. The first one is the spin value indices. If it's +1, it means we're looking at spin up plus K value. If it's -1, it means we're looking at spin down minus K value. We just have to look at one spin value at a time. And the layer indices is, so +1 means the bottom layer, -1 means the top layer. So the layer indices is actually transformed into the sublattice indices in the Haldane model. So as you can see in this MoTe bands, they can fit this model pretty well to the DFT calculations. The slight issue is that in experiments, twist angle is about 3.7 degrees. That's quite different energy scale. Because here in the so in the MoTe bands at 1.2 degree twist angle, the top two bands are pretty flat. You know, the bandwidth is about maybe less than 4 MeV. But once you increase the twist angle, the bandwidth will increase greatly. So that gives different energy scale. But nevertheless, the model here captures the correct topology and the energy scales for that specific angle. And in our work, we constructed an extended Haldane model for larger twist angles. So basically, we added a third nearest neighbor hopping. We still have the nearest neighbor hopping T0, the second nearest neighbor hopping T1, and the Haldane phase fixed by symmetry. We added a third nearest neighbor hopping. And because the third nearest neighbor, as you can see in figure A, red dots means one layer, blue dots means the other layer. The third nearest neighbor hopping in the lattice is going from one layer to the other layer. And this is interlayer tunneling. It didn't require a phase vector, so the third nearest neighbor hopping can be real. And so to get the correct energy scale, we plot our the energy dispersion against a DFT calculation from PRL. It's in D-Shaw's group. And with a set of parameters like T0, T1, T2 equal to -5, -1, and positive 0.5 MeV, we can get pretty nice, pretty similar energy scales. So our goal is to investigate if FCI emerges in such system. So to do that, we're going to use a composite fermion approach. Imagine we're not in the lattice yet. We're still in maybe two-dimensional electron gas with an uniform external B field. Composite fermion theory is saying that, oh, you have some fluxes in the system and some electrons. You can bind two flux quanta to the electron, and this composite thing will still be an electron. Sorry, will still be an fermion because the 2 is even. If you bind even number of flux quanta to an electron, it is still a fermion. And the composite fermion, by eating up this part of the fluxes, the composite fermion is experiencing a reduced field, as you can see, going from left to right. Some fluxes is absorbed in the composite fermion. We knew that in Landau levels, the degeneracy of energy level, or how many electron states you can host in one Landau level, linearly dependent on the strength of the B field. In a reduced field, one band now hosts reduced number of particles. This is great because by doing so, we can turn fractional filling of electron bands to integer filling of composite fermion bands, and then use the old language for integer quantum Hall effect. So now we're in a lattice system. It's quite different from Landau levels or free electron gas. Instead, we're going to do something called Chern-Simons flux attachment to each unit cell. So I mentioned before, we're attaching 2 flux quanta to 1 electron. So the relation is, so here's the illustration of the lattice. In 1 unit cell or 1 hexagon, we're inserting a phi. This phi, because we're inserting 2 flux quanta to 1 electron, this phi is linearly dependent on the number density of electrons. Here we're using 2n to denote that number density of electrons, and the other 2 means 2 flux quanta. And we can translate, so by rewriting the notions, now the inserted flux is 2 times the filling fraction of electrons. But in the experiments, they're doing hole doping. So eventually we're focused on the filling fraction of holes. So we also translate that to the relation between flux insertion and the hole filling fractions.
Question?
Yeah, sure.
Are you just inserting the flux by hand as if it is in magnetic field?
No, we have to construct a here. Sorry, can I? Yeah, here we have to construct a gauge potential and
Right.
do
What I'm asking is, at the level of your calculation, is there any difference between this calculation and, if I imagine, the system under magnetic field, is there any difference?
Well, system under magnetic field.
Well, I guess you're saying you're going to work with the Haldane model and give flux the way it is consistent with FCI.
We're working with Haldane model, which already has some staggering fluxes.
So
I'm
time
showing
reversal
that.
symmetry breaking is sort of given by, it's incorporated by using Haldane model. You're not going to get it through some spontaneous symmetry breaking.
Yeah, we assume that the spontaneous symmetry breaking has happened.
And it's captured by the Haldane model.
Yeah, we're only looking at one spin value at a time.
Okay.
Okay, thanks. Okay, so to incorporate this flux insertion to the Hamiltonian, we're using the Paros substitution. So we deliberately constructed a gauge field. So this is the potential vector. It's describing a uniform flux. And by adding a phase factor to the hopping strength, we can incorporate this flux insertion in the Hamiltonian.
But it's a still free fermion problem.
Yeah, sure.
It's a free fermion problem, right?
So after being mapped to composite fermion, we neglect the interaction. yes, free firm. Well,
A question, sorry.
on
I guess
lattice.
here it's an assumption that the flux attached is becoming a uniform field, like spatially
Yeah.
completely uniform, right?
Oh yeah.
Okay, that's part of the assumption. You cannot do a variation of the distributions. Currently, what you do.
That is an assumption, but I think if you want like space variation of the flux, you can construct different vector potential and still use the power substitution to incorporate that into the Hamiltonian, I think.
Right.
But Pyre subscription is just a way of, adding the vector potential. It's a way of incorporating the field. Why
Yeah,
is
yeah.
it flux attachment? I don't see any attachment in this.
So flux. Let's see.
I mean, you add, but then you spread it out, right? You spread the flux uniformly, and then
Yeah.
it becomes like a vector potential.
Yeah, exactly.
Just like what you do in standard composite fermion theory, after the mean field, of course.
Yeah, okay. Yeah,
Okay,
I'm waiting to see a calculation.
I mean,
Okay, thanks.
the fact that the gauge potential depends on the density
Yeah,
is the flux attachment, as far as I understand.
okay.
Okay, thanks.
Okay.
So after incorporating the flux into the Hamiltonian, one problem emerges, which is the original translational symmetry is broken because this phase factor in the power substitution has a periodicity that's larger than the size of the unit cell. And we're using a technique called magnetic unit cell. It's for example, if the flux insertion is a fraction P over Q, where P and Q are integers and co-prime, we can extend our unit cell Q times. And after doing that, the translational symmetry is restored. But the effect is that, the effect of doing this is that the Brillouin zone shrink to 1 over Q. So in total, we have in total the number of bands increased from 2 to Q, where the number of states in each band shrink by 1 over Q. So for each flux attachment, we have a corresponding filling fraction and power substitution to be incorporated into the Hamiltonian. We can diagonalize the Hamiltonian and plot the energy on the y-axis, and the filling fraction on the x-axis. This is the so-called Hofstadter spectrum. The blue dots are the energy values. The red curve in the first column of the figure is tracking the Fermi surfaces. And we also calculated this jump in the Fermi surfaces in the second column of the figure, and we call that composite fermion gap. So I'm only showing part of the spectrum. The whole spectrum has periodicity of 6 flux quanta, which is different from the original Hofstadter spectrum on a square lattice. By looking at the jump of the Fermi surface or the sharp peak in the composite fermion gap, we can find emergent incompressible composite fermion states. With the incompressible composite fermion states, we can calculate the total number of total Chern numbers that this state carries, and map this back to the Hall conductance of the electronic states. This is a simple relation.
So this
And
is integer quantum Hall effect for composite fermions. Is that what it is? Like the gap is built of composite fermions feeling some remaining flux or something. I'm trying to understand how what you're doing fits into sort of, you know, classic stuff, classic things that people have done in the past.
so let me think. So for a filling fraction of electrons or holes, you have so for a specific filling fraction, you have a set of composite fermion bands. And in the composite fermion picture, integer number of bands is being filled, and each band carries a non-zero Chern number. You can
Right.
sum them
Right. So
up.
it's an integer
to
quantum
get-
Hall effect for composite fermions, right?
Yes, integer quantum Hall
okay.
effect. Yeah.
Okay.
And
So the gap
and,
of the Landau level for composite fermions, your gap is that, right?
not exactly, because here the gap are not evenly distributed. Where
Because
in
it
Landau
talks
level,
better because of the lattice. Because it
yeah,
talks better.
exactly because of the lattice effects. Yeah. Okay. So in the composite fermion picture, just like you asked, we have language of integer quantum Hall effect with a total Chern number C. We can map this back to the electronic states and get the Hall conductance of the electronic states. And the expression is simple. It's C over 2C plus 1. And there are, sorry, yeah. So there are two types of fractional Chern insulators. The first one, so it's defined, well, we define it by the relationship between the Hall conductance and filling fractions. For Chern FCI, the Hall conductance is the same as the filling fraction times a unit. For fractal FCI, we define it by so for fractal FCI, the Hall conductance is different from the filling fraction times a unit. Okay, so we can look at the spectrum and find all those incompressible states and calculate the total Chern number and map this back to the Hall conductance of the electronic states. And we summarize that into a table, as you can see here in the table. There are two types of structures in the spectrum. So the first structure is there are some many small fractal structures. And the second one is there's a branch. So there's a Landau fan structure branching out from half filling. As you can see, these thin lines. So for JFCI, the detail is to the left of the half filling. Each composite fermion band carry a Chern number 1. So I'm not sure if you can see my cursor. So for 1/3 filling fraction, only one of the composite fermion band is filled. So total Chern number is 1. For 2/5, 2 composite fermion bands is filled. So total Chern number 1 plus 1 is 2. For 3/7 is the same. 3 bands filled, total Chern number 3. And they are translated into the Hall conductance of the electronic states as 1/3, 2/5, and 3/7, which is the same as the filling fraction. The same thing happens to the right of the half filling. And those are called JFCI. There's another type of FCI that emerges from the fractal structure. And they have different filling fraction compared to the fractional Hall conductance. But the problem is their gaps are really tiny, as you can see in the second column is at 1/5 to 7. The gap is tiny. So this indicates that observing them may need some more strict conditions like low temperature, higher sample quality. So this spectrum is at the specific hopping lattice parameters T0, T1, T2. And we'd like to know how robust is the FCI in terms of the variations of those lattice parameters. And here I'm plotting, I have a joint phase diagram for Hall conductance at 2/3 and 3/5 hole filling. This is important because those are the two filling fractions observed in experiments. So the axis, the x and y axis are labeled as tau1 and tau2 because we want to remove the effect of the scale of the T0 hopping. So we redefine tau1, tau2 as T1 over T0 and T2 over T0. So everything can be renormalized. So on the phase diagram, we found, so there are some numbers. They're in the form of Hall conductance for 2/3 and 3/5 filling. We found that there's a large area of Hall conductance that's the same as discovered in the experiments. Because, like I mentioned before, there's no direct measurement for the energy dispersion in experiments. So we kind of have to rely on DFT for the correct energy scale. But there are several DFT papers that doesn't fully agree with each other. So we hope that this large area of this phase can cover some of the variations in the DFT results. And here in this section, I'm going to discuss quantum phase transitions in this system. So for simplicity, in this slide, we're focused on a line in the phase diagram, which is this red line here. It's tau2 equal to 0. So we fixed the third neighbor hopping to 0 for simplicity. We also generalize it to the case without this restriction is in our paper in the supplemental material. So if you're interested, you can check that out. A quantum phase transition usually comes with the gap closing and reopening. In the Hofstadter spectrum, there are many fractal structures. They will shrink, expand, shift when lattice parameters change, giving rise to individual band touching and induce quantum phase transitions. Here we take the 2/3 hole filling as an example. At several hopping strength of tau1, the composite fermion gap closes and then reopens. Every time there is a jump in the Hall conductance. So for example, it jumps from 4/9 to 2/3 and then to 1/3 and back to 2/3. Other than that, we found that there's a Landau fan structure branching out at half filling that governs the composite fermion gaps for a group of FCIs. Actually, it's a group of FCIs includes every Jane FCI other than this 2/3 filling. So it's pretty extensive phenomenon. What's happening is that there is a higher order Fan-Hoff singularity at half filling, corresponding to this Landau fan. At half filling, the Chern-Simons flux per unit cell is 3 flux quanta, or 3/1, which means the rank of the Hamiltonian after Paris substitution is still 2. We still have a 2x2 Hamiltonian. We can decompose it into Pauli matrices, but I'm not going to get into the details of how those functions are. But by diagonalizing this 2x2 Hamiltonian and looking at the minimum of the lower band, we found that the energy dispersion is parabolic. And the coefficient is heavily determined by the lattice parameters. The parabolic dispersion means that at the minimum, the first derivative is 0, and the second derivative is influenced by lattice parameters, which could also be 0. Depends on which set of parameters you have. this leads to a higher order Van Hoff singularity because at certain set of parameters, this parabolic dispersion even goes to 0. And actually, the third derivative is also 0. We have fourth derivative. So a parabolic dispersion is already like free electron gas. And we can extract information about the effective mass from it. So the effective mass is in this form, is a constant over 1 plus 6τ1 times cosine theta. And so this is happening at half filling, but a small deviation from half filling is equivalent to a small change in the Chern-Simons flux, which can be related to a small external field delta B. So at half filling is parabolic at the minimum. So near the half filling with this external small B field delta B, the composite fermion bands become Landau levels with energy splitting. And this energy splitting, we call it delta LL, is inversely proportional to the effective mass and linearly dependent on the deviation of filling fraction from 1/2. So the thing is, when effective mass goes to infinity, this Landau level energy splitting will collapse, goes to 0. And since we have the
artifact, isn't this the artifact of using composite fermions? Like you're putting 2 flux quanta per electron. Is this have any way really? It's an artifact of using composite fermion, right? Because half filling is special for composite fermion, isn't it?
I mean, sorry, I didn't quite understand the question. Are you asking why?
At half filling, you're not getting integer quantum Hall effect for composite fermions, correct? Because you're putting 2 flux quanta per electron.
Yeah, exactly. Yeah, exactly.
Yeah. So whatever you see at half filling is a result of the choice that you make, choosing to work with composite fermions. That's not the only way to get a 1/3 quantum Hall state.
Yeah, you're right. So at half filling, we don't get integer filling of composite fermion bands, but this energy splitting will expand to those. Let me show you the spectrum. So yeah, you're right. So at let me see. Yeah, so looking at half filling, it's not it's not integer number of composite fermion bands, but we're looking at the structure at the minimum, and this structure is a Landau fan structure. It expands and reaches other filling fractions. As you can see, starting from the minimum of the half filling, this Landau fan structure extends to 1/3, 2/5, and 3/7, and every Chern FCI. So I'm not sure if that explains the question.
Okay, move on. Yeah.
Okay, thanks.
And Tian, do you think you can wrap up in about 5 minutes or so?
Oh yeah, sure.
Yeah, thank you.
Okay, so sure. So I mentioned that this effective mass can diverge. It goes to infinity, and here in this first figure, I'm plotting the boundary where the effective mass goes to infinity, and the red little star is the parameters we used for the Hofstadter spectrum I just showed. By increasing τ1 towards the positive direction, when τ1 is 1/3, is where the effective mass diverges. And at that set of parameters, the spectrum looks like this. So this Landau fan branching out from one half filling collapses. And also we expect a collective gap closing for every Chern FCI other than the 2/3 filling. So to test this scenario, we plot the composite fermion gap at 1/3, 4/9, and 5/11. So there are two types of curves. So the solid curves are the actually measured composite fermion gap, and the dashed lines are predicted by the Landau level energy splitting. We can see that at 1/3, the place where the gap closes is still a bit off by a small amount, because 1/3 is actually the farthest place, farthest fractional filling compared to 1/2. When moving closer and closer to 1/2, we can see that the composite fermion gap closes exactly as predicted by the energy splitting of this Landau fan structure. So the proximity to a so in the inset, I'm showing the Hall conductance of 1/3 filling fraction. You see that when the gap closes and reopens, the conductance jumps from 1/3 to 2/3 as a quantum phase transition. So the proximity to a higher order Van Hoff singularity provides a scenario to explore quantum phase transitions for a group of composite fermion bands induced by closing their topological gaps due to lattice effects, because the effective mass is controlled by the lattice effects. Guess I'm going to skip the summary. And here at the end, at this final slide, I'm going to show some interesting directions we're currently exploring. So with the help of an effective lattice model, we can now have efficient convergence of all kinds of algorithms that works on lattice. For example, here is a ED exact diagonalization results we have. It's on a 4x6 unit cells lattice with 8 electrons, so 1/3 filling fraction, and the ED results showing a 3-fold degeneracy, which is a characteristic of FCI at 1/3 filling fraction.
So this is without composite fermioning, right? The ED is without composite. ED is without composite fermion.
Yeah, exactly. ED. Yeah, ED is without composite fermion. Is with we are adding interaction to the system. Yeah. So with the help of a lattice model, it converges really quick. And we can also use the lattice model to do some density matrix renormalization group calculation. We can maybe measure the charge pumping or spin pumping. And another excellent work done by a group at Cornell is the fractional quantum spin Hall effect in the same system. So maybe by creating 2 copies of our lattices, we can build something that respects prime reversal symmetry and maybe see what's going on with the fractional quantum spin Hall effect. And maybe we can also add effects of displacement field to probe quantum phase transitions, because displacement field favors one layer other than compared to the other layer. And maybe we can explore something non-abelian. Okay, thanks. That's the end of my slides.
Any questions?
Not a question, more of a comment. Can you just go back to the summary slide and just leave it there?
Yeah, sure.
Right. Actually, I do have a question. So if you look at the model by Fensheng Wu and Alan, all of these people, so the two top bands which you want to capture, they're very well captured. I mean, their energies are well captured by this Haldane model, but the very curvature distribution is very different in this model compared to the continuum model. So what is the justification for using this to to model the actual system?
Yeah, very nice question. So, mm,
Just something to think about.
yeah, it's a very nice question. So, energy-wise, Chern number-wise, is the same. Yeah, in terms of So one thing is, it's so I think the fitting is done in a one-dimensional path in this two-dimensional momentum space, right? So it might not be able to capture the everything like energy, Chern number, and Barry curvature, but and also in our model with only third nearest neighbor hopping it doesn't look completely like the DFT calculations. So we currently we're adding more and more hopping parameters like fourth, fifth, sixth, so longer range hopping to first get the like energy wise and also like topology wise closer to that of the continuum model calculation, and we expect a exponential decay of those longer range hoppings. We're still working on that. But also, we think that DFT calculations are like they also depend on a lot of assumptions. The best scenarios, of course, we can find reference from the experiments, but now we don't have that. So we don't want our results to be a one-to-one mapping to a DFT results, because maybe tomorrow there's another DFT with another assumptions that has completely different stories.
I see. Thank you. Other questions?
Okay, thanks.
Maybe a quick question about the higher order Van Hove. Are they fine-tuned, as in normally, right? You have to tune a lot of stuff to make sure that you get to certain number of derivatives, something like that.
Number two. Oh, so like I mentioned, at half filling there's 3 flux quanta, and the Hamiltonian is still 2 by 2. We can solve this analytically, and looking at the so the minimum is actually fixed at one specific momentum. So we just have to look at that set of momentum kx, ky, and yeah, it's consistent for that kx, ky, and yeah, the dispersion is analytically parabolic like this, and it's dependent on the lattice parameters. Yeah, sure. Yeah, please continue the question.
Well, I guess because you said higher order Van Hove, usually, I guess generically it's not higher order, it's just quadratic, and you can fine tune it to be higher order. Is that how I should?
Yeah, sure. So we calculated this, and when so parabolic is second order, right? So when the effect mass goes to infinity, this coefficient goes to 0. So second order disappears. At the same time, third order is also always 0, and what's left with is fourth order. So k to the fourth order.
Questions? Okay, if not, then thank you, John, again. And,
Okay, thank you. Thank you, guys.